Welcome back to Old School Math. Today we're going to be taking a look at transformations with a vertical stretch or shrink. By the end of this video, you'll be able to graph a function that has been vertically manipulated and identify the vertical stretch or shrink when a function is in vertex form. Before we begin, let's consider the function f of x equals x squared, just our nice little parabola there. What would this graph look like if we doubled all of the y values? What would this mean for the y value then when x is 10, 100, and 1000? Let's go ahead and fill out this table together. So when x is 0, our function value of x squared is also 0. 0 squared is 0. When x is 1, the function value is 1. 1 squared is 1. When we substitute 2 in for x, we get our function value of 4. 2 squared is 4. When we put in 3, we get 9. 3 squared is 9. 4 squared is 16. And 5 squared is 25. Now if we did 2 times our x value, well, at first we might not notice a lot changing. So 2 times 0 squared, 2 times 0 times 0, that's still 0. But then on our next point, we see we have 1 squared is 1, and we have to multiply that now by 2 following order of operations. So 1 times 2 is 2. Here we'd have x squared, which is 4, multiply that by 2, you get 8. You get 18. 16 times 2 would be 32, and 25 times 2 would be 50. We see that this f of x equals 2x squared has greatly bigger numbers for y than our standard function y equals x squared, or f of x equals x squared. So in this case, we see that putting that 2 in there is going to make our function grow much more quickly, and it's going to make those y values much taller for the corresponding x values. Now, when x is 10, we should imagine a much larger number. If x is 100 and 1000, of course our function value here for f of x equals x squared would be very big, but 2x squared would be exactly twice as big. So this table shows us what happens when we introduce a scalar in the function. It causes the y value to stretch or shrink while maintaining the same overall shape of the graph. If the value is greater than 1, that means we're going to stretch it like we saw in the 2x squared example. It's going to grow much more quickly. It's going to stretch vertically. And if the value is less than 1, the exact opposite is going to happen. It's going to stretch, or it's going to compress vertically, or it's going to shrink vertically. That means it will grow more slowly. Imagine a piece of chewing gum. I think this is a funny example, okay? If you have a big wad of chewing gum in your mouth and you take it out and you stretch it vertically, what happens to that gum? Well, we know it gets taller, but it also gets more narrow. And a lot of people look at these graphs and say, hey, they actually get more narrow when you graph them. That is true, but I like to use the verbiage that it stretches vertically. If you take that same wad of chewing gum and you smash it down, we know that it's going to expand wider. A lot of people will see these graphs with a vertical shrink and say, hey, they just get wider. And that, again, is true. We're going to work these examples together, so go ahead and grab your note-taking guides and follow along. In our first example, we have 2x minus 1 in the absolute value bars. So this x minus 1, we should tell from the last video that that's going to translate to the right 1 unit. And this 2 tells us that it's going to stretch. So the parent function here is f of x equals absolute value of x. And the stretch or the shrink, well, that's going to be a vertical stretch. And it's going to stretch by 2 times. 2 times stretch. Okay, so if we look at our parent function, I'll just graph it real quick in blue. And I'll just do a couple points for us. So that's our absolute value of x. And then if we do a 2 times stretch on that, here's what's going to happen. The stretch is going to make this go, instead of being at 1 for our y value, it would actually be at 2. The vertex, of course, is not going to change because it's at 0. And then this value, instead of being at 2, it would double and it would be at 4. And this y value, instead of being at 3, it would double and be at 6. So what we see is the slope of this here actually changing. It's actually a slope of 2 now on this graph. Of course, I haven't accounted for this part of the equation. I haven't accounted for the translation to the right 1 unit. So what we want to do is take this green graph and just translate everything to the right 1 unit, including our vertex. So when we're graphing this transformation, let's review a couple things. First off, we said, okay, it's going to stretch twice as tall, so those y values get multiplied by 2. Also, we have to translate everything to the right 1 unit. So there's a couple things going on in this transformation. In this next example, we see we have f of x equals 1/2 the quantity x plus 2 squared. So this looks like there's a lot going on with it, and there really kind of is, but this squared up here tells us that it is a quadratic, so the parent function there is just f of x equals x squared. Now we know what that looks like. I'm going to graph that in blue, try and stay consistent for you. So our parabola starts at 0, 0, and we're just squaring every x value to get our y values. 3 squared is 9, it's up here somewhere. We'll just graph these first couple to be good. Okay? So that shouldn't look like any surprise to us. Now this 1/2, since it's less than 1, that tells us we get a vertical shrink, and it's going to shrink by half. And what this shrinking by half tells us that we're going to take all of our y values on this graph and take half of them. So half of 0 is still 0, half of 1 is 1/2, and half of 4 is 2. And you can see on this graph why people say they get wider. If we graphed our next point out, we said this one was up here at 9. Half of 9 is 4.5. So this would be graphed right here. And we see that it is slightly wider than our original function. Now the other thing we also want to consider is this plus 2. That plus 2 tells us that we have a horizontal translation of 2 units. We're going to go 2 units to the left. So I'm going to erase this green graph. We're going to go to the left 2 units. 1, 2. And the next one was at 2. So here's our new graph. We see that it is still wider than our original. In our next example, we see that we have f of x equals 3 times the square root of x. So the parent function is just square root of x. That should be pretty simple to see. And this 3 out in front tells us we're going to have a vertical stretch, since that's bigger than 1. So the square root of x starts at 0, 0. The square root of 1 is 1. The square root of 4 is 2. And we'll quickly put our parent function on our graph. So what we're going to do with this function is we're going to take all of our y values and we're going to multiply them by 3. So if we multiply 0 times 3, we're still at 0. If we multiply 1 by 3, we're up here at 3. If we multiply 2 by 3, we're up here at 6. So we see that this graph is now growing much faster than our original square root graph. There's no left or right translation because there's nothing in the square root with x. And there's no vertical translation either because there's no k value on the end that's added to it. Now real quick, before we log off, I have to admit, you can do these in a graphing calculator or on a utility like Desmos. That is not a bad thing to do to check your work. But it is helpful to understand when you look at a graph, when you look at a function, how it's been translated. And the vertical stretch is just if there's a number outside of our function that's going to make it grow faster or grow slower, depending on if it's greater than or less than 1. I appreciate you all watching this video. Hopefully this has been helpful to you. And if it has been, subscribe. And thank you for watching Old School Math.